What we're going to look at now are some of the things that affect the rates of SN1 and E1 reactions. Again, I'm going to pool the two together because they're very common. And the same things that affect an SN1, or I should say the rate of an SN1 will affect the rate of an E1. So let's look at the solvent effects in SN1. So what I'm going to do is actually compare this. Let's do a review. How did solvent affect an SN2? Well, an SN2 was favored by polar aprotic solvents. And the reason for that was that it actually raised the energy, didn't stabilize the reactants, so it kind of raised them in energy and shortened, and that's the way it shortened that activation energy, kind of broke down that hill a little bit. Now, SN1 is favored by protic solvents since it stabilizes the intermediates formed in the first step of E1 and SN1. Remember, what is the result? What is the intermediate result of the first step? So leaving group leaves, and you get a carbocation and that leaving group ion. So a polar protic solvent can help stabilize both of those charges. So if we look at a carbocation here, and let's imagine our solvent is water. So the negative part of water, the oxygen, is attracted to that positive charge. And with the leaving group, the hydrogen of water is attracted. And they basically solvate each of those ions. So if the energy of the transition, I'm sorry, the intermediates is lower, then the reaction will go quicker. So an SN1 is favored by protic solvents because it makes this hill, this activation energy, less than if it were in a polar aprotic solvent. Now let's take a look at substrate effects. First thing I want to look at is the um, effect of the leaving group. And I'm just going to compare the halides. So I'm going to compare fluorine to chlorine, and then bromine, and then iodine. Now, the least reactive leaving group is fluoride. The reason for that is that carbon-fluorine bond is really, really strong because fluorine's so electronegative. And then you'll notice, that as the size of the halide increases, so as you're going down the periodic table, fluorine and chlorine, so the size of the leaving group increases. And then iodine is the biggest of the halides, and it's the easiest one to leave. So it's the most reactive. But one of the primary effects of the reactivity in SN1 E1 when it comes to the substrate is carbocation stability. At the very bottom, we have methyl and primary carbons. Never want to show that. You cannot do SN1 on a methyl or primary. You cannot do E1 on a primary. That's never going to happen. Now, I will say, here's some important exceptions that I've covered in the past. If the primary carbocation can be stabilized by resonance, for example, let's say with an allylic position, if that leaving group leaves, you can resonance stabilize that carbocation. And that's okay. You can form that primary carbocation. Same thing. So again, this was allylic. If it were benzylic and primary, that can be resonance stabilized as well. So those types of primary carbocations are okay, but not if it can't be resonance stabilized, then you don't ever form it. Secondary carbocations are a little bit more stable. You'll sometimes see that do SN1, but the fastest of them are tertiary carbocations. So how would I, what's a good example of that you might see? So let's compare the rate of this reaction versus the rate of this reaction. Which one of those would react faster in an SN1 or E1 mechanism? Well, again, what I'm comparing is once that leaving group leaves, how stable is the carbocation? This would form a secondary and this would form a tertiary. So forming a tertiary is much faster. The activation energy is much lower for forming a tertiary carbocation than forming a secondary carbocation. Now, one other important aspect I want to talk about with substrate is that SN1 and E1 do not occur on sp2 centers. So for example, if the leaving group 1 an sp2 carbon, no SN1 or E1 occurs. If it's on benzene, no SN1 or E1 occurs. Okay, so and I want to emphasize that with all of the reactions we talked about in this unit. Substitution and nucleophilic substitution and beta elimination do not occur on sp2 or sp hybridized centers. We're just focusing on leaving groups that are on sp3 hybridized carbons. Now let's talk about the quality of the nucleophile or the quality of the base in SN1 and E1. Again, I'm going to start off by comparing this to SN2 and E2. SN2 was favored with good nucleophiles. E2 is favored with strong bases. And so it's pretty much going to be the opposite for SN1. SN1 is favored with poor nucleophiles. Okay, remember your list of poor nucleophiles like, water, alcohols, things without full negative charges. Now, hopefully you're kind of noticing the trend here. Those are also protic solvents. And protic solvents make the best solvents for SN1. Just kind of saying, make sure you recognize that trend. E1 is favored with weak bases. Okay, well, what are weak bases? All those things there, those protic solvents. All right, so that just kind of gives you an idea of things that affect the rate of SN1 and E1.